Hello everyone, here Juan Gea from Bone Studio, and today it's another well, no, not exactly. It's not another tutorial day. Today it's more like an overview tutorial day, because today we are going to overview the current status of the MantaFlow fluid simulator integration in Blender 2.79. So, as you can see, the build I have here, it's 2.79.1, but this is not a BuildBot build, because this is a build done by the user LazyDodo in Graphical, and he did the 24th October a build for Windows with the latest iteration of the MantaFlow simulator. So the author of MantaFlow simulation integration in Blender is Sebastian Vázquez, Sebas, and he's doing a magnificent job integrating this simulator. This simulator is going to replace the LBIM fluid simulation, the old fluid simulator, and the smoke fluid simulator. And today what we are going to see is the liquid part of the MantaFlow simulator. In another video, we will review or overview the current status of the smoke simulation part. So here we have, this is a fluid simulation done in MantaFlow, but what differentiates MantaFlow from LBIM? So for starters, in MantaFlow, we have fluid particles, but much more advanced fluid particles from the LBIM fluid particles. In this case, we have flip particles, where we can see those particles here. Let me disable the geometry. And we have flip particles. Here the particles are shaded with the velocity. So these are flip particles that are the most detailed particles in the simulation. We have drop particles, that are particles that are converted to ballistic particles, somewhat that way, based on its speed and on its effect on the simulation. One kind of new particle in MantaFlow is the bubble particle. So now we have bubbles inside the liquid. Finally, float particles, really useful to make some kind of foam and different effects. And tracer particles, that are particles that in this simulation, in this exact simulation, are not really obvious, but we will check this in other scene. And these tracer particles, what do is to keep track of the internal effects of the fluid, while the only part that matters to us is the flip particles, that is the external part of the simulation, the part that we see. So let's go to a new scene to check how can we use MantaFlow. Pool test. Okay, here we have a standard scene. Let me put this in solid, this in geometry or bounds. And here we have a standard scene. We have an object, a pool, that we will use as a collider. We have a sphere that will be our inflow object. We have a box that is going to be our mesh object. This is going to be a pre-existing liquid inside the pool. And we have our box or domain for the simulation. So about the domain, bear in mind that you should have the scale applied, so the simulation have the results correct. Another detail about the domain is that it's better to use in the dimensions, it has to be proportional, or proportional, because it has to be equal in its side, because the geometry simulation is going to be correct, but the particle simulation is going to be stretched if the dimensions are not equal in its axis. So with this done, we are going to see, be sure that you apply the scale in any object, for example this and this, so we don't get any problem. Okay, now we go to the simulation tab and we apply fluid MantaFlow. This is our collider, so effector collision. This distance is okay for now. Now this is going to be our pre-existing liquid, so fluid MantaFlow. flow, but instead of smoke, we select liquid, and instead of inflow, we select geometry. This way, we will get that volume of liquid. Right now, even when you see here mesh, it is going to fill up the volume, but the volume emission will be active probably in a future iteration of the simulator. But right now, we don't have any kind of volume emission. This is okay. Now we go to our inflow object. We are going to leave this inflow object disabled for now. And now we go to our domain, fluid MantaFlow, and domain. And here we have all the options. Be sure to change it from gas to liquid. Okay, now we see the box, nothing more. But what are the options that we have here? We are going to explain a few of all the options we have here, because this is an ongoing work, so this may change, or this could be unstable right now. So we are going to cover a small part of the options. So we have one important option, that is adaptive stepping. Let me show you what this means. We have this pool here, and we have this size, this voxel size. Okay, this is the voxel size that will be used to voxelize any kind of emission object or any kind of collider. So in this case, we can see that the wall of this collision object is thick enough to be correctly voxelized and to be seen by the particle fluids to collide against the collider. But in the case we have, for example, this situation, could be a cup of wine, for example. For starters, the voxelizer could not, may be unable to see this geometry or to correctly voxelize this geometry. And if it is correctly voxelized, it's possible that the liquid can't see this collider while it's moving fast. So to avoid this problem, what we could do, or what we should do, is to use the adaptive stepping. 4 is the default value, but we can decrease this value so the stepping is done more times per frame. In this case, 4 is okay. Now, in this video, we're not going to review this because this is more advanced, but this gives you the amount of particles you are going to generate inside the voxelization of the domain. Bear in mind that the flip simulation works in a different way than SPH or LBIM. What it does is that it calculates a vector field that gives us the simulation results, and it fills any voxel of the simulation domain with particles that later will be converted to geometry, to our simulation, or just to particles. So in this case, this is okay. And here we have the divisions. We are going to use 64, and as you can see here, we can get a preview of the domain resolution voxel size. In this case, for example, 64, to do a fast simulation now, it's okay. Now, this preview final, I used to use final, but probably in some simulations we need to use preview. But I'm not sure that this has any effect right now. Okay, and here we have the options to enable the particles, to see the particles. But let's rest this here and let's start this simulation. I'm going to hide this geometry because I don't need it. And Alt A, and here we have the geometry. Okay, let me put the domain in solid. And here we have this pool filled with water. Okay, we're going to bake it so we can review the results. This should bake fast. Okay, sorry. Free all bakes, 25 frames, just 25 frames. Okay, I think it's faster because we don't see the geometry being generated in real time, so the baking is faster if we don't see the viewport. Now we have a simple liquid. Okay, great. And why did I use just a fill of the pool? Because I wanted to show you the effect of these particles and the difference in simulation time. So free bakes, we are going to enable all particles. Automatically the domain gets configured to wire, but we are going to configure it to bounds, and you will see why in a minute. We are going to enable volumetric format for the cache, and here we are going to call it pool. Okay, bake. It's baking. It's a bit slower, not too much, but a bit slower than without the particles. And that's it. Go, go, go. Here we are. So here we have all the particles. And how can we check the particles? Here in particles, we have all the particles we want to see. Let's go to disable everything. And these are the flip particles. We can configure this to velocity. These are the standard particles. But if we check inside the particle field, if I move the view, I'm not sure if you can see this with the compression of the video, but this is completely empty. There are no particles inside here. Okay, so let's go to check another kind of particles. We have drop particles, that in this case are just the particles that are colliding and gaining velocity because of the collision, but not too much drop particles here. Bubble particles, that are the particles inside this volume because the collision, there's bubbles originating inside the liquid. Float particles, in this case I'm not sure why, but yes, these are particles on the surface of the liquid. Okay, you can see inside we don't have any float particles. And tracer particles, and those tracer particles are the particles, as I said earlier, keeping track of the inner simulation of the liquid, but with much lower resolution than the outer part of the simulation. You can get a pretty good explanation of how the flip simulation works in the talk Sebas gave in the Blender conference. I will put the link below in the comments. Okay, so we have this here. Now we are going to check how this behaves with some inflow. We go here, fluid manta flow, flow, liquid, inflow, and that's okay. So we can free the bake in case free your bakes, and let's resimulate everything. Now it's slower. It's baking. And that's it. If we go here and show the particles, we can see the particles being generated. Oh, the particles were not shown, so they were not baked. And this way we will see how the liquid behaves with an inflow object. As with the LBM simulator, we can enable or disable the inflow using the checker that we have here. Enable. We can animate this checkbox, and that's it. Now we go here and we get the full simulation with particles. Right now, I think we cannot do too much with the particles. I'm not sure if we can, at least in my experience, we cannot export the particles to Alembic and do such things. But I think this is an ongoing work. This will work at some point. If we disable, for example, the tracer, float, bubble, and drop, we get just the surface of the liquid or the bubbles generated by the liquid. Here we have the bubbles or the float particles. That's it. Okay, if we check the geometry generated, we go to solid, and here we have the geometry generated. Of course, we can increase the resolution here, or we can use the high resolution. Bear in mind, the high resolution, what does is a sampling of the domain, so it does like a subdivision of the domain in voxels. So it's not like doubling the resolution of the simulation. It's not going, as far as I know, it's not going to give us more simulation resolution, but it's going to give us more visual resolution. But I'm not sure if this is completely stable right now. So let's go to check another feature that we have here in the MantaFlow. I have a simulation baked already, swirl test, and here we have a swirl. Let me disable one thing I have here. This is not needed at all. Here we have a swirl. You can see it in real time. And to achieve this, we in MantaFlow, it's pretty easy. We just need to use, here we have the object, this object, sorry, and this object is a cylinder. And this cylinder is animated in this way. It's just rotating, nothing more, just rotating. And with this object rotating, we define this object as an effector, MantaFlow effector, but instead of being a collider, it's a guide. And this guide, what does is it is modifying the vector field, the forces vector field generated by the simulator, to try to adapt the simulation to our needs, to our artistic needs. So in this case, I wanted to do a swirl, and here we have the swirl. We can hide this, and we can hide this, and here we have the swirl. And the swirl disappears because the cylinder stops. Okay, here we have the cylinder is stopping, so the swirl calms down, and it's not happening too fast because the cylinder is accelerating. But this is pretty powerful because we can do many things. For example, Sebas in his Twitter has this example for smoke, and as you can see, you can drive the smoke to make the shapes you want the smoke to make. It's pretty cool. Basically, that's it for MantaFlow right now. It has some limitations. For example, I wasn't able to export this as an Alembic file to be used in the standard branch of on the release branch of Blender, so I can use this simulation to be rendered in Cycles in the branch we have installed in the render farm. On the other hand, this is not generating any kind of speed vector, so this doesn't work with motion blur right now. I hope this will be solved soon, but this right now is not working with motion blur. But that's it. If you want to see the result of this is a kind of a milk simulation. And that's it. I hope you liked the video. If you liked it, please press the like button, subscribe to the channel if you want to see more videos like this in Spanish or English, and see you in the next video, guys. Bye!